Hi, my name is dr. Ahmath. In this video lecture, we are going to talk about the logarithmic functions. So essentially, it is going to be the introduction to the logarithmic functions, and we're going to talk about why we actually need those logarithmic functions. So first of all, please let me remind you what is the inverse function. So if you remember, we've defined the function as a map or arrow which brings your number x from the domain to another number y in the range. So this is essentially just an arrow. And the inverse of this function is going to be the arrow which is going to bring you back to the x from the y. So this is going to be f. So this is essentially how the inverse of the function looks like schematically. So mathematically, we are going to define the inverse of the functions. Like if you're given f of x and g of x, if they are the inverses, then what should happen is that their composition should be equal to the x. So essentially, f of g of x should be equal to the x, and at the same time, g of f of x should be equal to the x. And essentially, this is one of the cool features of the inverse functions, and this is actually why we need the inverse functions. So essentially, if you're given some function f of x where the x is kind of like behind the other numbers, for example, x minus 3 divided to the 5, and if you need to just find the x from there or just cancel out all of the things around the x, you have to just apply the inverse of this function. So let's assume that I know what is the inverse of this function. So the g of x is going to be equal to 5x plus 3, for example. Now, if you just take the composition of these two functions, so essentially if you are given f of x, what you're going to do is you're just going to apply the g of x on the top of this. Okay, so it means that you just need to plug in f of x to here instead of x. So essentially, so it's going to be 5 times f of x plus 3, right? So, and then it's going to be equal to, so I'm just going to plug in f of x to here. It's going to be 5 times x minus 3 divided to the 5 plus 3. You can cancel this 5 and this 5, and what you have here is x minus 3 plus 3, and this is equal to the x. You see, so it's like every time when you have to deal with some equation and you need to get rid of the everything around the x, you need to apply the inverse. So, well, most of the time in the nature around us, we have the equations or the models which involves the exponential functions. So essentially, last time we talked about the exponential decay of the intensity of the radiation, for example, or the intensity of the light when you flash this onto the surface of the water. And all of these rules can be explained as the exponential decay rule. So essentially, the intensity of the radiation is going to be decreased using this law, let's say, e in the power of minus kt. Okay, so sometimes it is necessary for us to know what is the t. So it means I need to get rid of this exponential function. And one of the ways to get rid of those exponential functions is to apply the inverse of the exponential function. And we're going to define the logarithmic function as the inverse of the exponential function. So the logarithmic functions are the inverses of exponentials. Well, let's make the definition, the mathematical definition of the logarithmic functions. So essentially, so let a be a number which is not equal to the 1, then logarithm of x with the base a is defined as y is equal to the logarithm of base a of x. And it is true if and only if x is going to be equal to the a in the power of y. For every value x which is going to be positive. So for all of the values of the x which are positive. So essentially this is going to be the definition of the logarithmic functions. And I'm going to now do a couple of examples in order to explain you what does it mean. Uh, cool. So let's assume that previously we talked about the exponential functions, right? So for example, if I would write down the 2 in the power of 3 is equal to the 8, right? So if I say, hey, what is the third power of the 2? And it was more or less clear how to find this because you just need to multiply the 2 itself 3 times. And now what I'm going to ask you this question, hey, so I'm going to write down the logarithm. Here I'm going to write down the answer, and here I'm going to write down the base of your exponential function. And I'm going to ask you, hey, what is the power of 2 which gives you 8? What is the power of 2 which gives you 8? Okay, so it's not so easy to find, right? So you need to know that if you multiply the 2 itself like 3 times, you're going to get the 8. So you're going to write down the 3. Or for example, if I would ask you the question like, hey, what is the log of 4 and 64? And again, the question is, you need to always put the question like, what's the power of 4, which gives you 64, which gives you 64. Okay, and this is going to be equal to the 3, right? So the logarithm of 464 is equal to the 3. It means that 4 in the power of 3 is equal to the 64. So what I'm going to do is I'm going to write down the schematics of the logarithmic forms and the exponential forms of the numbers. So essentially, if you have the logarithm of ax is equal to the y, so this is the logarithmic functions, right? And an exponential function is going to be a in the power of y is equal to the x. Okay, so please note that it is going to be the exponential function, and the basis of the exponential function and the logarithmic functions are going to be the same. And the exponent, if you remember, of the exponential function, it's essentially the power of the exponential number or the base, right? Is going to be here on the right-hand side of your logarithmic function. So it always helps you um, to figure out the logarithms, to calculate the logarithms. So the cool feature of the exponential and the logarithms is that they are the inverses. So essentially, these two functions are the inverses, and they should fulfill the algebraic properties of the inverse functions. So essentially, if you're given one function, f of x, to be equal to the logarithm of ax, and at the same time you're given g of x, which is going to be a in the power of a in the power of x, then the composition of these two functions should be equal to the x. So essentially, f of g of x is going to be equal to logarithm of a, right? So instead of x, I need to substitute g of x, which is going to be equal to the logarithm of a in the power of x, and this is equal to the x because of the property of the inverse functions, because they are the inverses. And at the same time, we can just show that the g of x or g of f of x is also equal to the 1. G of f of x, which is going to be equal to, now instead of x here, I'm going to put the f of x, so a in the power of f of x, and this is going to be a in the power of logarithm of ax, and this is also equal to the 1. And this because the logarithmic function and the exponential functions are the inverses. So let's try to figure out a couple of, let's do an example to try to use this. So essentially, do you remember in the beginning I told you, hey, we need the inverse functions in order to get rid of the things around the x, right? And one of the ways to get rid of the logarithms, for example, to use its inverse, which is exponential functions. So let's do an exercise. So let's say you are given logarithm of base 4 of 5 plus x, and this is equal to the 3. And let's assume that I need to solve this equation. In order to solve this, you see, so I need to find x from here, right? So we need to get rid of this log, okay? So I'm going to write down the function f of x is equal to the log 4 of x. Could you please tell me what is the inverse of this function, right? So do you remember here? So the scheme, right? So the inverse of this function is going to be the base, right, in the power of x. So essentially, the inverse of this function is going to be 4 in the power of x. So these two functions are the inverses, okay? So what I need to do is, in order to solve this equation, I need to get rid of the logarithms. In order to get rid of the logarithms, I'm going to apply the exponential function from both of the sides. So what I'm going to do is I'm going to put the g of this thing from here and g of 3 from that side. So essentially g of 3 from this side. Okay, so essentially I'm going to substitute the argument x of the g of x with this number, with this expression, and with this expression. So this is going to be 4 in the power of logarithm of 4, 5 plus x is equal to the 4 in the power of 3. Then we know that this is going to cancel this one because they are the inverses, right? So it's going to be simply 5 plus x. It's going to be 4 in the power of 3, which is 64, right? Then I'm going to find x from there. It's going to be 64 minus 5, which is going to be equal to the 50. 9. So this is how we are going to solve the equations which involves the exponential functions and the logarithmic functions. And one more thing, which is really important, is that so whenever you find a solution, it is always necessary to check your answer by just plugging the x to the equation. So essentially, let's do this. So the logarithm of base 4 of 5 plus 59 is equal to this 3. Is that true? Yes, we know that this is true because the logarithm of 464 is equal to the 3. So in the beginning, I told you that hey, the exponential functions are going to cancel out the logarithmic functions. Uh, yeah, so the exponential functions are going to cancel out the logarithmic functions, but it works in a vice versa direction as well. So the logarithmic functions are going to cancel out the exponential functions as well. So let's say I've got so if you remember, our first examples of the exponential functions was about the how the population of the cells are going to increase, right? So let's do another exercise. So let's say the number of these cells after t hours or after t hours is going to be equal to 10, the initial number of the cells, 2 in the power of t. Okay, so for example, if you would like to know what is the number of the cells after 5 hours, you just need to put the t2 there. It's going to be more or less straightforward. It's going to be 32 times the 10, which is going to be 320. But at the same time, I would be interested to know. So let's say you know that n is equal to the 300 or 640. Let's say 10 times the t in the power of t is equal to the 640. And I would like to know what is the t. Okay, so in this case, again, so I'm going to just put this 10 to the right hand side. It's going to be t in the power of t is going to be equal to the 64, right? And now I need to get rid of this t in order to find the t. And one of the ways to get rid of the exponential is to use its inverse, which is logarithmic function. Again, I would like to write down the functions that f of x is equal to the t in the power of x is the exponential function. And the inverse of this exponential function is going to be logarithm of base t of x. So these two functions are again the inverse functions. And if I would like to get rid of this t, I need to just apply its inverse from here and from here. Okay, so this logarithm is going to cancel out this exponential, and you will have simply t from here on the left hand side, and on the right hand side it's going to be the logarithm of 2 and 64, which is going to be equal to the 6, I guess. So this is the reason why we need the exponential functions, the inverse function, sorry, and in particular the logarithmic functions, in order to solve the equations which involves the exponential functions. So in our next video lectures, we're going to discuss about the properties of the logarithmic functions, their graphs, and the equations which involve the both logarithmic and exponential functions.